Riemann sums and definite integrals. Taken from the previous section, we've actually done all the work there. And so what we were trying to explain in the previous section, in terms of the area, was exactly and identically Riemann sums. The definition that we had given for the area before, based on the rectangular slices, trying to find the area under the curve, those slices, and add them up with the summation, that was the Riemann sum. Here we want to give a more exact and formal definition for the integral. So the Riemann sums, again, take this function, for example, f of x equal to the square root of x, and we want to look at the area under the curve. We take these rectangular slices that we call intervals or subintervals. They're based on a partition. The partition, you recall, is based on slicing each of these pieces into the same width, that is b minus a divided by n. The definition of the Riemann sum: let f be defined on some closed interval from a to b, and let delta be the partition of a to b. And delta, you recall, is b minus a divided by n. And we want to shrink the partition, make these rectangular slices as thin as possible. Thus, we're able to find an accurate depiction of the area under the curve. These partitions are equally divided from a to b, from x naught less than x sub 1 less than, and so on, less than x sub n minus 1 less than x sub n, where a is equal to x naught and b is equal to x sub n. These intervals are the small subintervals given by the x sub i's. We pick a number on the subinterval, from each subinterval, from x sub I minus 1 to x sub I, some number c sub I, where c sub I is actually a point on the function, to be able to calculate then the so-called summation, or the Riemann sum, the summation as I goes from 1 to n of f of c sub I times delta x sub I, here where c sub I, again, the same information from the previous section. C sub I is on the interval between x sub I minus 1 and also less than x sub I. We say that the regular partition is given as this delta x, or the norm of delta, which is b minus a over n. We then talk about a definite integral, and then we can give the definition for the definite integral. Here, to define the definite integral, consider the limit. Well, this is the same limit that we've discussed before. You may say, well, we talked about the limit as n goes to infinity. Well, the partition going to 0 is a more stronger statement. So here we say that when the partition here gets smaller and smaller, this implies that n is going to infinity. The stronger clause here is this statement here. Well, we know that delta x, which is being represented by the delta, that is b minus a over n. So obviously, as n goes to infinity, you do see that the delta is going to 0. As b goes to infinity, as n goes to infinity, b minus a over n goes to 0. The statement here, as the partition gets smaller to converge to 0, obviously it does force n to go to infinity. What does that mean here? This limit as the partition goes to 0 of the summation f of c sub I times the width. F of c gives us the height times the width. We say that this is a limit possible. Well, how is it a limit? If there exists here some delta positive, such that for every epsilon that we have here, this measurement between some number L, some real number L, this measurement between L and the summation is said to be very small, less than epsilon. If this is the case, irregardless of the choice of C sub R based on the partition, then we say that here the limit exists, and thus the integral is some number. So what is the definition, therefore, that we can prescribe for a definite integral? Here we say that that f is defined on a closed interval a to b, and the limit of the Riemann sums over the partitions delta is given by this statement here. That this exists, then f is said to be integrable on the closed interval from a to b, and the limit, if f is integrable, then it has a limit, and the limit is some finite number. Now, it is possible for the function to be integrable, and the limit could be described as being a very strange notion. But for this course, we will talk about things that are measurable, and so we talk about functions that are indeed integrable. A function is integrable if that function is continuous. So here, this limit of the summations is equal to this integral from a to b, f of x dx. How do you know that you have endpoints from a to b? Well, it comes from the partition, you recall, because the partition is said to be b minus a all over n. The limit is said to be called the definite integral of f from a to b. We call a the lower limit of integration and b the upper limit of integration. We just say a and b are the limits of integration. Continuity implies integrability, that if the function f is continuous on a closed interval, then f is also on that same interval integrable. That is, that the integral exists. The definite integral here described as the area of a region under the curve. If f is continuous and non-negative on the closed interval a to b, then the area of the region bounded by the graphs of f, the x-axis, and the vertical axes x equal a, x equal b, is that integral. And here's the diagram to denote that the function, but we're talking about the area under the curve. And so this region under the curve, by adding them up with those rectangular slices from the Riemann sums, gives us the area. There are several properties, very neat properties for integrals. Here in particular, a definite integral. If you integrate here, if f is defined at x equal to a, if you integrate from a to a, you're not going anywhere, so obviously the area is 0. If f is integrable on a closed interval from a to b, then the integral from b to a of f of x dx, see how you flip that? So obviously you want to negate if you integrate from a to b. So this is the integral from b to a f of x dx. Well, it seems to be backwards because the integral should be measured from least in terms of the x values to the greatest a to b. So if it's swapped with the limits of integration, then you can just negate here the integral. And it doesn't matter. You can always do that swapping and just negate the integral. The additive interval property, that if you want to slice up the intervals, if you got some big interval from a to b, the integral from a to b of f of x dx is the same thing as integrating from a to c, f of x dx, plus the integral from c to b, f of x dx. some more properties of integration. These two properties define the integral as being a linear algebra. That's important. Here, the integral of the constant times the function, f of x dx, is the same thing as pulling out the constant times the integral. So here we call the first one, this is scalar multiplication. And then the second one would be in terms of vector addition. We can look at the integral as being a vector. You integrate over a vector, we get the result of vector. So here, this is said to be vector addition. It could be addition or subtraction. Doesn't matter what direction you're adding in, as long as you always add. So the integral of the summation of the sum of f of x plus or minus g of x dx is the same as the integral of f of x dx plus or minus the integral g of x dx. So the integral of the sum is the same thing as the sum of the integrals. That's what that says. Let's move on. Let's look at this problem here. The first one is to integrate using the definition. So what we need here is to extract first the partition. You recall the partition here, the delta x, is said to be b minus a over n. So this would be 4 minus 1 over n, or 3 over n. We need to pick c sub I. I will use the right endpoint. So we say that this is a plus I times delta x. Remember, this is the same setup from the previous section. Matter of fact, this problem is being worked by identically the information from the previous section. So here, the a is 1 plus I times 3 over n. And so this is 1 plus 3i over n. So now this integral from 1 to 4 of 4x squared dx is said to be the limit as the partition shrinks of the summation as I goes from 1 to n. Here, this is 4 times f of c sub I times this delta x of I, which is the same as the delta x. And so this is now the limit as delta x, the norm of that goes to 0. The norm is said to be just the measurement, the length. Summation as I goes from 1 to n. This is 4 times, now here this f of c sub I becomes, it's that x squared, but x, so x here becomes the c sub I, so this is 1 plus 3i over n to be squared, and the delta x is 3 over n. So this is the limit. Here we can look at that as, this implies that n is going to infinity. Take the 4 times the 3 and just get a 12 out in front, times the summation as I goes from 1 to n. And so this is just 4 of this. This is 1 plus 6i over n plus 9i squared over n squared. And this is times 1 over n. So this is the limit as n goes to infinity. This is 12. If we lose the summation, Now remember, this is a summation of 1 to, I'm adding up 1 plus 1 plus 1 plus 1 n times. That becomes 1 times n. So this is n times that 1. And this is plus that 6 times I. And I becomes n times n plus 1 all over 2 times that n there. So this is 2n plus 9. I squared, you remember, is n times n plus 1 times 2n plus 1. That's over 6 times n squared. This is all times 1 over n. This is the limit. As n goes to infinity, don't forget we have the 12 there. I'm going to distribute that 1 over n through. So this is 1 over n times n. I get 1 plus, this is 6 divided by 2. That's just a 3. And we're multiplying this n downstairs. So this is n squared plus n all over n squared. Plus the 9 divided by 6 becomes a 3 over 2. And then this 2 here would cancel out the 2 downstairs. So this is a, maybe I need to leave that. So just say this is just 3 halves. And up top we have n times 2n. So that gives us 2n to the third. Plus we 4 that. That's 3n squared plus n, and that's all over. We simplify the 9 over 6, so this is n squared times n to the third. Now you see the biggest term that's going to attribute from this fraction is the 3n squared divided by n, which just becomes 3. And then over here, the biggest term here, the other terms would go to 0. The biggest term here was that 2n to the third. That's going to be divided by this n to the third. So then from there times the coefficients. So the limit of this 12 times 1 is 12. The limit of this term would be 3. This is n squared divided by n squared, so that limit is 3. And it's times the 12. Plus, the biggest term here is the 2n to the third divided by 2n to the third. So that leaves me with a 3 here. And all the other terms would be something divided by n or divided by n squared. So that limit would go to 0. So this becomes 12 times 3 as well. I hope that's fine. I hope you see that. This term here goes to 3 times the 12, right? This 2 would cancel out with this guy. And so its limit here is 3 times the 12. I hope that's a good depiction. So we get 36 plus 36, 72 plus 12, 84. Here in this exercise, sketch the region whose area is given by the definite integral, then use a geometric formula to evaluate. So they want us to graph this. So this is y equal to x, and you're going on the interval from 0 to 4. So this just gives us a triangle. This is 4 because y is equal to x, and this is 4. So the area for a triangle is 1/2 times the base. No. 1/2 times the base times the height. So that gives us 8. So we calculated just using the graph. So this is y equal to 3x plus 4. And you're on the interval from 0 to 2. So if x is 0, then we get 4. And if x is 2, we get 6 plus 4 is 10. So I'll draw this in. Not so good on my drawing. Let's see if I can outline it with blue. Oops. It's a trapezoid, right? It's a trapezoid, and you recall that the area for a trapezoid is 1/2 times the base times the first height plus the second. So this was 10 up here. This is 4, right? So 8 sub 1 is 4. 8 sub 2 is 10. Then the base is 2. It's pretty big 2 there. So the graph is not drawn to scale. How about that? So this is 1/2 times the base, which is 2, then times the sum of the heights, 4 plus 10. And so that just gives us 14. All right. So y is equal to 1 minus the absolute value of x. And then the interval is from -1 to 1. You recall from Math 112 and from Math 100 that this is the absolute value graph. Has the graph of a v. It's negative, so it's going to be upside down v. 1 is going to be its height on the x, or the y-axis, excuse me. So this is 1, and this is -1. That's 1. So this is a triangle with base equal to 2, right? So the base length is 2, and the height is equal to 1. So the area for a triangle is 1/2 times the base times the height. This is 1/2 times the base, and the base is 2 times the height, and the height there is 1, and so all we have is just 1. Well, what about this one? These problems in exercise 33 to 40, evaluate the integral using the following values. So here they just tell us that if you know that the integral from 2 to 4 x cubed dx is equal to 60, can you use that to your advantage? If you know that the integral from 2 to 4 of x dx is equal to 6, can you use that? And then the integral from 2 to 4 of dx is equal to 2. Well, let's see. And this guy, see, this interval is going from 4 to 2. That's backwards. It needs to go from 2 to 4, right, of x dx. We had a property that says that you negate that value if you swap the limits of integration. Well, we know that the integral from 2 to 4 x dx is equal to 6, so this becomes negative 6. What about this one? I'm integrating, I'm not going anywhere, right? From 2 to 2, well, that's 0. Now this one, let's pull out the 8. This is times the integral from 2 to 4 of x dx. And do we know the integral from 2 to 4 of x dx? I think they gave that to us, right? The integral from 2 to 4 of x dx is equal to 6, so we use that. We have here 8 times 6, 48. And that's all I have for you. Thank you.